I personally know Alexios when I was a PhD student, and he did very pioneer work for the Polo codes and algorithm and efficient hardware implementation. So you may know that right now the Polo code has been adopting the 5G standard. So behind that, there's one effort from Alexios. Okay, so let's welcome his talk.
Thank you for the introduction. Well, yes, we worked actually on very similar topics during our PhDs, and we did them kind of in parallel. That's how we know each other. And now, since I was in the general area, let's say, nearby by North American standards at Cornell, I thought, why not pass by and say hi and maybe present some of the things. So about half of this presentation is actually the things that Bo mentioned about hardware implementation of polar decoding. So the first half is actually about that. If you have questions, feel free to interrupt me. I mean, you can do it interactively, it's completely fine by me. So let me quickly explain first one of the terms that are here in the title. Maybe not everyone is familiar with it. This what I mean by this happy scaling era. So by that I refer to the, let's say, 20 last years, where the rate of improvement of integrated circuits followed very closely like the rate of increase of throughput and decrease of latency and increase of energy efficiency in communication systems. So these increased requirements were relatively easy to be met because circuit technology followed kind of the same trend. So new ideas, more complex signal processing algorithms were relatively easy to actually implement in practice. Now in the last few years, this is not that true anymore. So obviously integrated circuit technology is still progressing, but at a slightly lower rate, while communications the requirements of communication standards keep increasing at similar rates than before, maybe even higher actually. So yeah, this is what I mean by this term specifically. And what I want to convey today, like the message is that if we want to continue the progress that we have done in the past years in terms of implementation of signal processing algorithms, we will need to attack this problem from many different angles. So first of all, the classical algorithm hardware co-design that was done and is being done is actually more important than ever. And also we have to look at other layers of abstractions and possibly even other disciplines in order to get ideas that can help us implement these signal processing systems with like reasonable complexity. So as I said, there are two parts, let's say, to this presentation. The first one I will talk a bit about this classical algorithm hardware co-design, and I will do so by taking the example of the implementation of decoding algorithms for polar codes. So I will talk a bit about the hardware implementation of successive cancellation list decoding of polar codes specifically. And this is the decoding algorithm. This list decoding algorithm is the algorithm that is used as the reference for the performance requirements, the error correcting performance requirements in the 5G standard. So this is a very important algorithm for the standard. Then I will also talk a bit about the different algorithm that we proposed and also implemented in hardware, which is called successive cancellation flip decoding algorithm. In the second part, I will talk a bit about how we can use tools from information theory and machine learning in order to, again, improve from an implementation perspective these signal processing systems. So we can use these tools in order to reduce the complexity, basically, of the algorithm itself, and at the same time of the hardware implementation of this algorithm. So the keyword polar codes was in there many times. As Bo already said, they're quite interesting at the moment because they were included in the 5G standard. So they will be used specifically to protect messages on the control channel of the 5G standard. There are many other innovations in 5G, obviously, but these advanced channel codes, including polar codes and LDPC codes, are one of these innovations. And this is why also we were interested in looking at this problem. Now, to give you a very brief introduction to polar codes, what they are, how they work, and how they're constructed. So let's say that we want to construct a polar code of block length n bits. And in order to do so, if we want the rate of the polar code to be r, that means that in each block of n bits, we need to have n times r information bits. This would make the rate exactly r. So this is done by taking a subset of these indices, 0 to n minus 1, and by loading information bits into these indices only. And the remaining bits in the code word, or in this vector here, are actually frozen to some value that's known at the transmitter and the receiver. And this is usually 0, just for convenience. Okay? Now, the way in which we select this subset is very specific to polar codes. This is what makes a polar code, how we select this subset. I will not go into details about this, but there are very specific ways in which we can systematically construct these codes. Then this vector that is constructed here with the zeros and the information bits is encoded by multiplying it with a generator matrix. This is a binary matrix. And again, the generator matrix of polar codes has a very specific structure. Because of this structure, the encoding can actually be done with n log n complexity. Even though it's a matrix vector multiplication, it can be implemented with n log n complexity. It has structure that looks very similar to the structure of an FFT. Like it has these butterfly structures. And this is why the complexity is also the same. FFT is also n log n. The resulting encoded vector x is then transmitted over some memoryless channel. And we receive, at the receiver side, a noisy version of that code word, which is y. And the job of the decoder is obviously, given this noisy version of the code word, it needs to decode the information bits. That's what the decoder has to do. Now, the algorithm that's used in practice to do this is called successive cancellation decoding. As the name suggests, possibly, this decoding algorithm first decodes like this first information bit, then it uses the decoded value in order to decode all the next bits. That's why it's called successive cancellation. It's like a successive interference cancellation that's used, for example, in MIMO and so on. It's very similar, but it operates on a bit level. Now, this decoding algorithm is very powerful asymptotically, so if you let this block length go to infinity, then you can prove actually with this decoding algorithm, even though it's suboptimal, that polar codes are capacity achieving. So asymptotically, it's very good. At block lengths that are of interest in practice, the decoding algorithm is not that good. It works, but it's usually worse than other competing codes like turbo codes or LDBC codes, for example. So it's not that competitive in practice. But to give you a somewhat better idea of how it works, so this is the kind of graph structure that I mentioned previously that looks a bit like an FFT. On the right-hand side, we have the noisy channel observations. On the left-hand side, we have the decoded bits. Some of these bits have known values. They're the frozen bits. So some of them, we already know that they should be 0, the first 3 and this one over here. The others have to be decoded. And to do this decoding, we basically combine all of these channel outputs through this graph in a very specific structure. In order to get at the output here for each one of these bits, we get an LLR, log likelihood ratio, which can then be used to decode that bit. The colors here correspond to the 2 operations that have to be done to do this processing. They're both very simple. One down here is simply an addition or subtraction with this very simple arithmetic operation. And the other one, if we do like an approximation that is used a lot in hardware, it's basically just the multiplication of the signs of 2 incoming values times the minimum absolute value of these 2 incoming values. This is also used in decoding of LDPC codes and many other applications. It's known as the min-sum decoding algorithm. So it uses exactly the same updates. So if we want to implement this in hardware, this can be done actually with a relatively simple architecture. So we have, here you see 3 main components. The first one is this one here, this decoder core. So this contains simply hardware that can implement these 2 update functions that I showed you before, the F and the G update function. And it contains many of these. In particular, we have P, because many of these operations can be done in parallel. Not all of them, but many can be done in parallel. So we want to parallelize this as much as possible to make it as fast as possible. Then we have the memories. These memories store all the, well, first of all, they store the noisy received code word because we need that to do the decoding. And then they also store the internal messages inside the decoder, because every time we activate one of these nodes in the graph, it produces some output message which has to be stored because it's then reused later. And so this is what the memory does basically. And then we have a simple controller that just organizes the read and write addresses in the memory based on which bit we are decoding. And that's more or less what it does. We also have here a small block where we can write the indices of the frozen channel. So we can tell this decoder which of these channels are frozen, so which bits have value 0. So, and because this is programmable, this thing can actually decode polar code of any rate. With a small modification, it can also decode polar codes of any block length that is smaller than a maximum block length, and the maximum is given by how big this memory is, what we can fit in there. But because of the structure, it's actually very easy to do that. So in that sense, the architecture is quite simple. It's very flexible in terms of rate and block length. And because it's so simple, it turns out also when you implement it, it's quite compact and very energy efficient.
So is this like ASIC or is it more like a...
So what I show here is like it's a block diagram, it's a high-level architecture, but we have ASIC results for it as well. We did not implement this particular decoder on an ASIC, like we don't have the chip. We have all the results, I mean, all the steps before actually sending it to a fab, but then fabbing it can be very expensive, so we do it selectively. We have not fabbed this, but the decoder I will talk about next, the list decoder, we have it on the chip actually. Yeah. Yeah, so I said before that one of the problems with this SC decoding algorithm is that the error correcting performance is not that good compared to other codes. The other problem that I already mentioned a bit is that it's difficult to achieve high throughput because, as I said, some of these operations can be parallelized, but not all of them. So this thing is very sequential because it needs to use previous bit decisions. So these are the main challenges with this decoding algorithm. Now, in the next few slides, what I would like to address is the second challenge mainly. There's very good work done by many other groups about the first problem. So this has been, I would say it has been solved. So there are many ways to speed this up very significantly. Now, what I want to talk about is this other kind of decoding algorithm, successive cancellation list decoding. The main problem with the simple SC decoding algorithm is that if some error appears somewhere during the decoding, this cannot be corrected later because we never revisit that bit decision. We take it once and that's it, and then we reuse that decision. So this error can never be corrected, and it can even cause more errors later due to error propagation. Now in SCL decoding, list decoding, we don't just decode one candidate code word at a time, but we actually decode L possible candidate code words at the same time. And these L code words differ in some of the bit decisions. So some of these bit decisions are actually different. This means that if some error happened somewhere during the decoding process, in one of these candidate code words, hopefully there is another one where this error did not appear. So, in the end, we can select either the most likely out of these candidate code words, so we just compute the likelihood of each code word, or what is done commonly in practice is that a CRC is added into the code word. In the end, we can do a CRC check, and with very high probability, only the correct code word will pass the CRC. Now, to illustrate this a bit better, we can use this structure that's called a decoding tree. Each level corresponds to a code word bit. So here we have U0, U1, U2. And then every bit that is not frozen, that's an information bit, actually has two possible values, 0 and 1. The bits that are frozen have only one possible value. So for example, here U0 is frozen. The only option for the value of U0 is 0, basically. So the SC decoder, if we look at it on this tree, it follows only a single path. So when it reaches this kind of one information bit, it has to take a hard decision to go left or right. And then it does the same thing at for every information bit. And at some point it will reach a leaf, and then we know that this path here corresponds to the frozen bit. If we take all the labels, 0, 0, 0, 1, 0, 0, 1, 0, this is the decoding code. Now list decoding, on the other hand, once it reaches this first information bit, it will not take only one direction, but in this example where the list size is 2, it can actually follow at the same time both directions. And that's the main idea behind this. And then it continues in the same way. So every time we reach some information bit, for that information bit there are 2 options. Since there are 2 active paths, this means that we actually have 1, 2, 3, 4 possible candidate paths to continue with. And a selection is done based on which one of these 4 paths is most likely, and we continue with these 2. So it's actually possible to, if we have these 2 paths here, it's possible to discard one of them completely. So we could, the next step, it's possible that this path here is thrown away completely. We actually only continue with these 2 because they end up being more likely.
So how do you decide when to not trim and when to trim?
So you always trim at every step in this decoding algorithm. At every step, you have 2 L possible directions, and you always keep L. So you always trim in this algorithm.
So you
there are variations of this that are adaptive and they don't always trim. But in the simple version, you always trim.
So here you go to U3 and then you go both left and right?
So yes. So at the beginning you go both left and right.
Uh-huh.
And then you go to, well, U4 is frozen, so it only has one possible value.
Right.
And then when you reach U5, you expand actually both of these, this one and this one. And then it's possible to compute the likelihood of each path.
Right, and then you, out of 4, you trim two.
You keep the 2 most likely.
You keep it.
Yes.
And it could be in both sides.
Yes, so you could have one here and one here. In this example, I keep only the 2 on the left. But it could be any one of these forms.
So it's a fixed L.
Yes.
There's no like a threshold.
Well, there are more advanced versions that have a threshold, and maybe, so these different information bits also have different reliabilities which you can calculate.
Right.
So maybe you want to do the splitting only for the bits that are not very reliable.
Right.
And people have done this in practice. But this is the most basic version of the algorithm. You can do things adaptively, yes.
So if L were 4, you would keep the 4 candidates. Right?
Yes, so if
then you would trim further.
for L4 you would keep 2 because it's still smaller than 4. And here you could actually keep these 4. And then you would trim down to 4.
Then you would trim.
Yes, exactly. Yes, that's how it works. So to implement this decoding algorithm in hardware, it's useful to see what changes with respect to simple SC decoding, so that we can then adapt the architecture that we already have for SC decoding, which is quite good, so that it also supports SC list decoding. So the main differences is that we have to do all the computations for L paths in parallel, and that we need to compute these path metrics that I mentioned before, and we need to sort them, or we need to find some other way of keeping the L best paths out of the 2 L candidate paths. In practice, L is, common values are, let's say, 4, 8, or 16. So this sorting procedure may not seem very difficult. You don't have that many values. But if you want to do this in parallel, in hardware and in parallel, it can be quite significant. And the main problem is that you cannot continue decoding before you do this sorting. So if this sorting takes too long, it makes your entire decoder much slower.
So it's like bookkeeping is an issue, right?
Yes.
I remember, yeah. I guess like what's the problem is you try to, if you push this through some sort of like pipeline network, you always have to resynchronize and then do comparison and then decide.
Yeah, so the way we implement it, actually there is, like we have L parallel pipelines, let's say, which are by construction always synchronized. So the paths finish the computations at the same time always.
Yeah, because it's fixed.
But you could overlap in some weird way possibly, but then always you have to wait at some point until you have all the path metrics so you can select and then continue.
Yeah, so there's no point about going faster and all that.
No, it doesn't really help, no. One thing that people have done is, so you don't necessarily need to sort all of these path metrics. It's sufficient to find the L smallest ones, actually, which can be done a bit with slightly more simple circuits. And this is a bit simpler. And then while you're continuing with the decoding, you can take these L smallest values that you found, you can sort them in parallel to the decoding. Because in the next step, you need to have them sorted.
Second, you find the L smallest without sorting them.
So, yes, you don't do a full sorting, basically. You only find the L smallest, which is a bit less than actually doing the full sorting.
Right.
And then you can continue decoding because you know which paths you should keep.
Right. You don't have to.
And in parallel to the decoding, you can quickly, at the same time, sort
sort
the list.
which you'll need later. Yeah.
Yes, exactly. You sort it in parallel with decoding. So this saves a bit, but it doesn't make a huge difference.
Yeah, it doesn't seem.
Yeah, it doesn't make a fundamental difference. It just makes it a bit faster in practice. So yes, these are the two main things that change. The nice thing here is that the computations for the paths can be done in parallel. So if we are willing to have a bit more hardware, this actually doesn't add anything to the latency. We can do all the processing in the same time, more or less. So for this reason, the architecture that implements this decoding algorithm looks very similar to the one for SC decoding. The main difference is that instead of having one decoder core here only, we have L in parallel. And then you need to also multiply all of these memories because you have L paths that you need to store. The only one that doesn't need to be replicated is this, the channel memory that has the noisy observations, because this is common for all the paths. And this is actually quite significant because each one of these memory blocks here has the same size as this channel memory. So you're saving quite a bit by doing this. This is a nice property of the algorithm. And then the other significant thing that is added is this block that does the metric sorting, basically. So one important contribution, I think, and this may be one of the things you had in mind when you introduced me, is that we showed, and actually you showed the same independently in parallel, that you can reformulate this decoding algorithm in an arithmetic domain that is different than the arithmetic domain that was used in the original paper where it was described. So you can do this decoding using log likelihood ratios instead of likelihoods, like it was described in the original paper. And this can help the hardware implementation tremendously. In terms of the algorithm, the two formulations are equivalent. It doesn't change anything. The performance is exactly the same. But for the hardware, these LLRs can be quantized with significantly fewer bits. Their dynamic range is much smaller. And also you only need to store one number, one LLR, instead of a likelihood for the case where the bit is 0 and another likelihood for the case where the bit is 1. So overall it makes a huge difference, and for the list sizes we looked at least, it can make the hardware implementation up to 67% more hardware efficient. Hardware efficiency is a specific metric. It's measured in megabits per second per millimeter square of chip. So it's a specific metric that basically compresses the two metrics of interest, which are the throughput and the area. So this way you can compare decoders that have different areas and different throughputs.
So basically, what's going to happen is your internal LLR memory is smaller. Is that?
Yes, all of these memories, everything that has to do with LLR, so these memories.
Because your quantization is.
Yes, which is most of the memory. Most of it is LLRs. Everything is smaller. Also, these circuits here that do the arithmetic operations have smaller bit widths because the LLRs have smaller bit widths.
Of course.
The path metrics have smaller bit widths, so everything becomes smaller and faster at the same time. So it affects almost the entire decoder, except for the controller. This is the same. It doesn't change with the arithmetic formulation. And this this path memory here that just stores bits also doesn't change.
And the CRC is at the end, or you can make a CRC in the middle of the decoder that's long?
Yeah, so we use a CRC at the end, but then there's a lot of work where people have tried to find other places to put their CRC where maybe it's better. And the most interesting thing is probably that you can split the CRC into smaller CRCs.
Right.
You don't need to have one big 16-bit CRC. You could have smaller CRCs here and there.
Right.
Which can tell you, first of all, if decoding failed, you will know it earlier.
Early on, yeah.
So you can stop if you want, or you can do other things.
Yeah.
And then it's also possible to do this list decoding only partially. So you don't do it on this entire FFT-like graph that I told you, but you only have multiple paths for a part of this graph.
Yeah.
This is where you can use the multiple CRCs, because at some point you will have L paths, but at some point you need to shrink it back to 1, so that you can then expand And you can use the CRC somewhere in between to shrink it to one path, or no paths if it fails completely. And then you can continue with list coding. So there are many variations on this.
And also there's a parity check version.
What?
Instead of CRC, they use a parity check.
So some bits, it's not a CRC, but a single parity check or something.
Yeah, like a parity check, like syndrome type of.
Sure. I mean, you could assign some bits that are, it doesn't have to be a CRC necessarily. It's just the CRC is very good for detecting errors.
Yeah, it's very powerful.
Yes.
But if you maybe use parity check, you can make it simpler.
Yes. Or possibly you could even correct some things in there.
Yeah, you could correct, yeah.
Yes, yeah. Yeah, all of these variations exist in the literature. I mean, people have looked at all of that. These are good ideas and they can help a lot in some cases.
Oh, it's a hot topic.
Yeah.
Save some money.
Yeah, sure. So yes, I talked about the metric sorting. This is actually quite important because, as I said, you cannot continue decoding before you do this sorting. So the path metrics, when we use the LLR-based decoder, actually have some properties. They're not arbitrary numbers, but they have some very specific properties. I will not go into the details of the properties, but you can use these properties in order to simplify different sorting architectures that exist in the literature. These are not new, these have been known since 40, 50 years, but they can be simplified significantly, so you can remove many of these comparators in there, and you can even remove some comparator stages entirely. And this is interesting because if you remove an entire stage of comparators, this is what decreases the latency, the delay through the circuit. This is why this is interesting. So this reformulation is also very useful to simplify the path metric sorting step. Now, I said I will talk also about another decoding algorithm. So in list decoding works well in terms of the error correcting performance. It's very powerful. But the bad thing, let's say, is that most of the computations that are done in there are kind of wasted most of the time. Because even the simple SC decoding algorithm would be able to correct the error. So this is a downside in some sense. So what we observed initially in simulations is that when you do SC decoding, if you look only at the frames, the code words that were not decoded correctly, and you look at the distribution of the number of errors inside that code word, actually, in most cases, it depends a bit on the SNR, but in most cases, you have a single bit error inside the code word. There's only one bit that's wrong. And this destroys the entire code word, and in a real receiver, it will probably be thrown away and retransmitted or something like that.
What channel do you use?
This is all AWGN. Yeah.
If you have a bursting channel, maybe a difference to it.
So if you have a channel that has, where the quality of the channel changes within the code word, then this may look different, yes. Sure, yeah. But then if you have a block fading channel,
The whole thing will.
the whole thing, so if you have a block fading channel, it's a bit like just like picking one of these. It's like changing the SNR, if it's block fading, in some sense. But all of these results are with AWGN. Yes, we haven't actually looked at others. So yes, the idea we had is quite simple. So the successive cancellation flip decoding algorithm first does one round of SC decoding, which in most cases is sufficient. Then at the end, we add the CRC, just like in list decoding, to check if it was correct or not. If it was not correct, then we allow the algorithm to restart. And this time, we do the decoding slightly differently. So we have saved from the first decoding iteration the T most unreliable bit decisions. This you can do in many ways, but we just looked at the LLR magnitude. This tells us something about how reliable the bit decision is. And then once we reach one of these unreliable bit decisions, we just flip that bit and continue decoding normally. And this hopefully, the idea is that it hopefully identifies this one decoding error and we can correct it in the end. So this works quite well in practice. The error correcting performance is better than SC decoding, of course. And it can match SC list decoding with a list size of 2 or 4. It depends a bit on the scenario, on the code rate, and so on. But it can be quite close to that. The memory complexity is exactly the same as that.
So you're like freeze, right? When you say you flip, then it's like freezing, right?
Freezing in what sense? So if in the first run of SC decoding the bit decision was 0, in the second trial we change it to 1.
You just fix it to 1.
Yes. So we ignore the LLR that comes
yeah.
there. We ignore it. We say, okay, this probably failed before, so we just flip it. Yeah, exactly.
But you have to run the whole thing again, right?
You have to run the whole thing again, yes. You could, depending on how you implement it, you could start from the bit that you want to flip and then continue. So you don't have to do the entire decoding.
Right, because
But
it's
this,
like
I mean, yeah.
sequential, yeah, but it's bookkeeping and it's...
It is a bit tricky, yes. And it doesn't save you that much. I mean, it's easier to just have a simple architecture that doesn't need this bookkeeping and all this stuff, and that you do the entire decoding again. Because you do it rarely.
Right. But it's really like freezing, right? So there's nothing special you have to do, right?
No, you don't have to do anything special.
Right.
The only thing you have to do is that the first time you decode, you have to keep track of these most unreliable decisions. That's it.
Yeah. And the next time you use the original T or you get the new T?
The next time you use the original. There are also versions of this that get a new T, so they can do, effectively they can flip multiple bits at the same time, like this. But we use the same. We use the same T. Yeah.
So you rerun the SDF to T times instead of the 2 to the power of T times.
2 to the power of T would be
Because
if you check all
Combinations.
Yeah, sure.
Because for the chase decoding for like the real solo of this age, typically you will use 2 to the power if you have fixed the n unreliable decisions, and then you rerun 2 to the power.
Yes.
Well, it makes sense like going like to 2 or like to 3 bits, you know, but like 2 to the T is a lot if T is 8, you know.
It depends on how you determine the value of T.
So the T that we use is, for example, in some simulations we use 16.
16.
So there 2 to the T would be a bit too high.
Would be too
Yes,
high, yeah.
exactly. And also because of this distribution we saw here, it doesn't make sense. You will not gain much.
Right.
Maybe if you go to 2 or 3, yes. And people have gone to 2 actually. So people have generalized this to 2 and 3, and they found good ways of actually doing this, because it's not completely trivial how you go to 2. And that helps a bit. But then if you go beyond that, you don't gain much. And yes, the last point is that the average time complexity of this thing is very close to SC decoding, because at relatively high SNR you have very few errors. So if your bit error rate, your block error rate is 10 to the minus 3, you have errors rarely.
Once in a blue moon you have to redo.
Exactly. The disadvantage is that the execution time is not deterministic.
Yeah.
It's variable. Right. This can be a problem.
Yeah,
so this is the clear disadvantage.
There's no guarantee on latency.
Exactly. Yeah. Well, you can guarantee a maximum.
The
worst case.
Yes. The worst case. Right. But the worst case is very bad because T's, as I said, can be 16 or something like that. So the worst case is very bad, then it's not representative. So, I mean, it's not useful to talk about the maximum.
Well, it's going to depend on the application.
Yes. So this is the clear disadvantage, which can be a headache if you want to integrate this into a bigger system.
So when you say you give us examples here, right? Do you have in mind the length of the code
for
some of these results?
So here, I mean, we mainly use the 1024 bits for all of these results, yes.
Okay.
Because at the time it was the standard that was used, the standard block length in all publications in the area. Then it makes it easier to compare if you use the same block length.
1024 coded or uncoded? What's the rate?
Coded and rate 1/2 usually.
Rate 1/2.
Again, because this is what almost everyone used for no reason.
Yeah, I'm just curious. You know.
The 5G standard actually uses shorter block lengths, 256, 512. So a bit shorter, yes, a bit shorter than that.
Because the ultra reliable. Because it's for control channel.
It's for control channel, so you don't have that much data.
Control channel, right?
So for a shorter block length, you need fewer of these. I mean, T can be smaller to get the same performance gain, because you have fewer possible bits that can be wrong.
So you work with Borg?
Yeah, he was my PhD advisor. Yeah. So yes, and okay, then if we want to implement this in practice, if we start from the SC decoding architecture, what we need to add is really minimal. We need this We need a kind of LLR sorter that just tells us the T most unreliable bit decisions. And then we also need a CRC unit, which the normal SC decoder doesn't need. It doesn't need to decide if decoding was correct or not. It just decodes and that's it. So it doesn't need the CRC unit. But this is really negligible in terms of area. There's no impact on latency. We don't have to wait for anything to continue decoding. Actually, in one of the 3GPP meetings for 5G, the decoding algorithm was mentioned as a possibility for using in very low power modes of operation, mainly the ones that are for IoT. And then, again, the standard usually defines a reference performance. It doesn't say you should use this algorithm, but it uses, so they say that the performance should be at least as good as a list decoder with a list size 8, for example, for this particular block length. So it's used as a reference, and then you can implement it as you like.
So right now, for the standard of the scenario of the MMTC and the UILC has not determined the ECC candidates yet.
No, I don't think so.
Right now, only the EMMB determines.
Huh?
Right now, only the EMMB.
Yes.
Yeah, determines
so.
the LDPC and
And for the others, I don't know when they will be determined. I don't follow this much because if you read through this, it's a bit crazy. If you read through these documents, I mean, they're very long and they're very detailed. It's very difficult.
Did they accept Polar for the control channel?
Yeah, for the EMMB,
yes.
Because 5G have the 3 scenarios. EMMB is for the enhanced
Yeah.
mobile.
This is normal data.
The multi,
And for this, the MMTC and another UILC,
Yeah,
not finished yet.
That's not finished, right?
Yeah,
No.
not finished.
No.
But for control for EMBB, they have accepted Polar
Follow
codes.
officially.
But what decoding, or does it matter?
The
Decoding
reference is list decoding
list-
with list size
Just decoding.
8, I think.
8, right?
Yes.
Yeah.
It also depends a bit. There are so many modes, so it depends. It's not always the same reference. It depends a bit on the mode. There are different block lengths.
Different code rates.
It's a big mess. But the reference is list decoding in general.
Yeah.
Yes. Yeah.
But is it only polar for the control for EMDB? I think there is another thing.
That's a good question. I'm not sure if it's only polar.
Was it also turbo?
I think they
Turbo
had
is
some
not in there at all.
LDPC,
It's LDPC and
yeah.
polar.
And for,
There was a small length LDPC. I think I remember.
It's
somewhere.
possible. And the LDPC codes that are used for the data,
data
I
channel.
know that they're very flexible in terms of rate and block length.
Yeah.
They have hundreds of different combinations.
Yeah,
different
that I
options.
remember. Was it tail biting convolutional?
That had been abandoned. There's some companies they once tried to propose that, but I remember that because about a while or 2 years ago I tracked a lot for those.
Yeah, I
programs.
tracked, but I'm older than you, so
Yeah.
I forgot more.
So those are tail convolution that they have been implemented.
Yeah, I remember, yeah.
Do you remember who proposed that?
I can't remember, so many companies.
Yeah.
And the right aside, the last time I tracked that for the UILC, so it seems that right now the Polo kind of be more advantaged than the LDPC.
Yes,
Yeah.
yes.
Even for those, some companies previously they supported LDPC for the EMMB, but for the UILC they submit some evidence that Polo looks superior to LDPC.
Right. Yeah, I remember sort of that.
There's a technical side and a political side in these meetings.
Yeah. How powerful is Qualcomm? How powerful is Huawei?
Yeah.
I think they compromise. in
They
the end.
They compromise. Yeah.
They compromise in Canada. So the one interesting aspect of all this, one of our students when I arrived here in 2000, she was a student of Roy Yates. She was doing the Ericsson simulations for the thing. And Ericsson was trying to be independent, and she was like trying to be the independent comparator of all the types of algorithms.
When she evaluated all proposals that came in.
Well,
from,
whatever
or
kind, you know. But
the ones that make
I
sense.
think she went crazy, you know. And she changed job after that.
There are so many
imagine.
proposals at each standard meeting.
I imagine.
Yeah,
I went half crazy just trying to read these things. I mean,
Yeah.
imagine having
Yeah.
to do the simulations and
Right.
write a report about it.
Right.
Yeah. It's a bit crazy. Okay, good. Maybe I will skip directly to the. I will skip a bit this part because we had a good discussion, but I don't want to keep you for too long. So this had to do a bit with implementing these decoders on unreliable hardware to save power, basically, and how we can analyze the decoders that operate on unreliable hardware. But I can give you the slides if you're interested, and you can have a look.
So what is your application and thought for unequal error protection? Like what do you have in
So
mind?
this is unequal error protection within the decoder. So you have this memory that stores the LLRs, and you implement a part of this memory with a reliable circuit that is normal power, let's say, not high power, but normal circuit. And you can implement, with this scheme, you can implement a very large part of the memory with a low reliability circuit that is low power, consumes less area, and so on. And well, you can show some asymptotic results that you can, the decoder is still asymptotically powerful, that it can give you reliable communication, so you can have zero error rate, basically, asymptotically, but at a lower rate, so it doesn't achieve capacity anymore. But it's unequal error protection inside the memory. It's not for the code, nothing to do with the code word bits.
So you're, in your decoder you use a memory with less power and then the bits that you store can be flipped? Is that
Bits,
what
well, this analysis is for binary erasure channel, so yes, the messages you store inside the decoder can be erased inside the decoder. So it's not just the channel that erases the bits, it's also the decoder internally that can erase.
So your block diagram, the LLR memory, which memory gets?
So the LLR memory,
The LLR memory.
yeah, which is the biggest memory in general.
Right, and
So the analysis is for LLR memory.
So when you get erasure, is it a 1-bit erasure or is it like a block erasure? Or?
No, it's not a block, it's a single message inside the decoder. So it may not even be a bit.
Single message?
Yes. I mean, in the case of the BC, it is a bit, yes. In the case of the BC, these LLRs have only 3 possible values.
All right.
And one of them is an erasure. And we say that you can have the other 2 values, which are the correct values, can be erased inside the decoder, because your memory is unreliable. And there are actually memories that
But
are...
you have to know it's erased. In erasure channel, you know that it's erased.
Yes, inside the decoder, yeah, you could know, but we don't use that knowledge. So we don't assume that you know actually inside the decoder.
So it's really not a erasure channel. In
It's,
erasure channel, you know it's erased.
Yeah, in that sense, maybe it should not be called an erasure channel, but a ternary output channel that has like very specific transitions that are only allowed. So you can have, from a 0 you can go to a 0 or to an erasure. From a 1 you can go to a 1 or to an erasure. In that sense it's like an erasure channel.
But then you know.
But you don't know.
You don't know that
Inside the no, I mean you could know, but we don't use that knowledge anywhere.
it's like the voltage is high or low or something close
Yes,
to
so
zero.
there are memory cells actually that can have 3 states. So it's one high, one low, and one in between. And the in-between one is the one that's usually less reliable, so you can use that to represent the erasure. And then it's possible that you fall either from the high voltage to the in-between or from the low due to some disturbance. Can be radiation, can be many things. And this is then the erasure. It's the 3rd state, basically, that is the erasure.
So then
And to call it an erasure channel, you're right, you should know it in principle that it is an erasure. And you could know it in the decoder as well, but for all the analysis we did, we didn't use that knowledge.
So you model basically your storing of the LLRs as a channel.
Yeah, exactly, yes. Which has some probability of destroying your LLR, basically. Yeah. And with some unequal error protection, some other tricks, you can show that you can still use this in practice, actually. It can still give you, under some conditions, a reliable decoder. It has the same reliability as before, but you cannot use it on a very noisy channel. So the channel has to be less noisy for the decoder to work. So in essence, somehow the internal errors translate into channel errors somehow. You can map it into a capacity
Can you
reduction.
map? Yeah, okay. So
In
you
this
can-
case, yes. In this case, yes. So with this particular error model. Now, if you have something that's more detailed as an error model, it's difficult to say. I haven't done this, I don't know.
Well, this is very interesting.
We can discuss it more later. I mean, I have all day. It's not a problem.
Sure.
Let me skip maybe to just the last part that has to do a bit with machine learning, and it's for a different communications application as well, so that we don't limit ourselves to coding only. So traditionally, to implement a bidirectional communications link, we either do time division duplexing or frequency division duplexing. That's the most common way, or a combination of these two. There's been another way that's now around for a few years, that's full duplex communications. So here we use the same frequency band, and the transmission and reception happens at exactly the same time. So there's clearly a very strong self-interference from the transmitter to its own receiver, because they're not using a different resource to transmit and receive their signals. So in order for this to work, this self-interference has to be cancelled somehow. Now, in principle, it should be relatively easy to cancel that self-interference, because it's caused by a signal that's known. I mean, a node is causing interference to itself, basically. So it knows what it transmitted in principle.
Echo cancellation.
Yeah, it's echo cancellation, but it's an extreme case where the echo is super strong. It's not an echo like in DSL lines, for example, where it comes from the other end, it comes back. It's an echo that comes directly from the transmitter to the receiver. They're separated by...
In theory, the stronger the interference, the better for you, if you had the dynamic range.
Yeah, yes, if you have the dynamic range, but you don't have it usually.
Yeah.
So you have maybe I mean, if we look at the ADC at the receiver,
Right.
it's usually 12 to 14 bits.
Yeah.
So your dynamic range is in the order of 60 to 70 dB.
Yeah.
And the self-interference is usually stronger than that. I mean, if you compare the level of the self-interference,
80, 90 dB.
it can be much higher. It can even be 100 dB stronger than the thermal noise, or than the signal that you're trying to receive, which is more important probably. So it's a very extreme case of echo cancellation, yes. Yeah. So the problem is that in practice, you know the digital signal, but you don't actually know exactly what the self-interference looks like, because there are many analog components, amplifiers, mixers, and so on, that introduce a ton of nonlinear effects into the signal. So most of it is a linear function of the digital transmitted signal, but there is a significant part that's a nonlinear function of the signal. Now these nonlinearities obviously make the digital cancellation of the signal quite difficult, but it's possible to do it. It's possible to model these effects using some of these polynomial models to reconstruct this nonlinear self-interference and then to subtract it from the received signal. So this is a model that's used quite a bit in practice. It has a few problems. One is that it has quite a few terms. It has many of these parameters that have to be estimated, and it has these basis functions that are powers of the transmitted signal. This power can be quite high. It can go up to 9th power, for example, and so on. So it's a bit of a nightmare to implement this in terms of DSP.
Well, come the Finnish group. Finnish group.
Yes. Yeah, sure. They've done a lot of work on this. And recently I've also worked with them a bit, so they gave me some data sets actually to try some of the ideas.
Yeah, very nice. Volterra series.
Yes. This is not the Volterra. Volterra series is even worse. This is a parallel Hammerstein model.
Okay.
And this also includes IQ imbalance from the mixer. So it's kind of an extended parallel Hammerstein model. They've also used the Volterra series in one paper, and it works a bit better, but the complexity just explodes. And you have way too many terms to calculate. So the very simple idea that we had is, of course, instead of writing down this model, estimating all these parameters, and computing all of these basis functions, many of which don't contribute much to the result, to actually have a neural network that can learn this. From the same training data that we would use to learn these parameters, it can learn the entire function. That is the hope, at least. Now, to make this a bit more realistic, we actually do the cancellation in 2 steps. So we first do linear digital cancellation. So with this, we can cancel using standard digital signal processing techniques, the linear part of the self-interference, which is usually the strongest as well. And then we subtract that from the received signal, and what is left is the nonlinear part of the signal, plus some noise, clearly. And this is what we're trying to model using that neural network. So only this nonlinear part of the self-interference. And the neural network is super simple. It's the most basic neural network you can think of. It has an input layer, one hidden layer, one output layer. The input layer, we feed in the real and imaginary parts of the digital transmitted signal, and a few delayed versions of that, because there's memory in the system. And at the output, we get the real and imaginary part of the reconstructed nonlinear self-interference signal. This is what we want to subtract in the end from the received self-interference signal to cancel it, hopefully. Now, we use some measured data from a testbed that we have in the lab. It's a 10 megahertz of FDM signal with QPSK modulation. It's not very important what the signal is exactly, but we wanted to compare the two approaches to see what their performance is in terms of cancellation. So the green line here is the polynomial model that I showed before. This pinkish purple is the neural network. If you look at the power of what's left after we do the cancellation, for both cases it's more or less the same. So they give us the same performance in terms of how well we can cancel the echo, the self-interference.
Minus 90 almost.
Yes, so it doesn't quite reach the noise floor. We have these, I mean, the main thing that is these 3 dB come mainly from these weird peaks here. Yeah. The one in the middle is kind of makes sense. It's carrier leakage or something like that. Right. We understand why this is there. But the others here on the side, we don't know where they come from, actually. They're not, it's some intermodulation, I don't know what this is. But it's not a function of the transmitted signal, and that's why it cannot be cancelled. So this is a bit weird, but it mainly comes from here. The rest is really almost at the level of the thermal noise. And the thermal noise is, so we run an experiment where we don't transmit anything and just record what's received. And that's our effective noise floor of the receiver.
What's the blue?
The blue is what you receive before you do the cancellation. That's the echo. It's the power spectral density of the echo, the self-interference.
Oh, okay, so minus 70 is relative. No, it's not relative to that.
No, this is absolute power here.
Okay.
Yeah. So we receive this because what I didn't say is there is also some analog cancellation before that. Because if you don't do that, you have dynamic range problems. Clear. But here I'm focusing on the digital cancellation only. Okay. That's why the echo is at minus 46 dBm. Right. The transmit power is actually at 10 dBm. So we have a 56 dB of cancellation in the analog domain before anything.
How is that done? Before
it's digitized. How we do that? In our setup, we have one transmit and one receive antenna that are just spaced a bit apart, and this already is sufficient to give quite a bit of isolation. In practice, there are more advanced methods you can do it with. Active. I mean, this is just passive, basically. It's isolation between the two. But there are also active ways of doing this. We just don't have one of these implemented in the lab, so we use the passive method to kind of emulate an active method. It would have the same effect. Now, they have the same performance, but what's interesting is that the complexity of the neural network based approach is much lower. So if we count the number of additions and multiplications that are needed to implement this in digital signal processing, we have 67% fewer additions and 30% fewer multiplications for the neural network-based approach. And this we also implemented actually on an ASIC, not manufactured, but we have the final results placed and routed and everything, but we did not manufacture it. And here if we compare the area, we see that the neural network-based canceller is about 11% smaller, and its throughput is about 60% higher, so it's much faster. This is partially because it requires fewer multiplications. So if we instantiate the same number of multipliers, we can do all of these multiplications in fewer cycles, so it's faster. But it's also partially because it can run at a higher frequency, because it requires a lower quantization bit width actually to give the same performance. So this polynomial canceller needs about 23 bits, if I remember correctly, to give good performance. The neural network can get away with only 17. This is also another reason why it's faster in the end, because the operating frequency is higher.
So your ADC is 17.
Huh?
You said your ADC is 17 bits?
No, this is the quantization that's used for the signal processing internally. The ADC is 14 bits of this testbed specifically. But internally, especially because you have these powers of X,
Right,
you need actually more bits. And we try to reduce the bit width in this canceller so we use a block fixed point architecture basically, where different powers are shifted by different amounts so that we only keep the important part of the result. And then when we add them up, we shift them back so that the decimal point is at the same place, and then we can add them up together. So we spent some time also optimizing this baseline architecture. We're not comparing the neural network to a polynomial implementation. That's very bad. We spent some time to optimize both of them.
So basically, what you decided, you could have used less area but have a smaller throughput, but used a similar area but got a bigger throughput.
So the area is smaller and the throughput is higher at the same time.
I know, but,
Yeah.
but compared to how many multipliers and adders, you could have less area, even less area.
Ah, yes, sure. So you could instantiate fewer of these multipliers, so that you get maybe the same throughput, and then the area would be much lower. Yes, you can trade these things almost as you want. I mean, there's a lot of freedom, especially because this neural network, well, it has a neural network structure, so you can schedule the operations in many, many different ways. And with this polynomial canceller, that's not exactly the case. I mean, the granularity with which you can do these trade-offs and change the complexity is much finer within neural network. You have so many ways how you can do which order you can do the processing, how many of these you can do in parallel, and so on. So it's much easier with this one.
And this adaptation has to be done like when you transmit per bit or per whatever. How do you like per transmitted?
So here for these experiments we do it offline. So we do this transmission, we record the data, and then we do the estimation and everything offline, and the training of the neural network, because this has to be trained.
But based on how long you.
So here we use the training data size here was 16,000 samples for both of them, both of these.
Divided by 8 oversampling, or how many symbols?
It's oversampled by a factor of 2, so the bandwidth here is 10 actually, it's from -5 to 5, and it's oversampled by a factor of 2. So the sampling rate here is 20 megasamples per second.
So basically you.
So it's not, I mean, in terms of time, it's quite short. But so we didn't evaluate, maybe you can actually get the same performance with way fewer training samples. We didn't look at that. The goal was not to look at the training, I mean, it's an important issue, but we didn't do that here. We just wanted to have a size of the training data that gives us good performance for both of them, and then we just fix that there. And anyway, the size of the training sample doesn't affect these numbers here. These numbers, this is only for the inference, let's say. It's after you've already done the training, how quickly can you produce cancellation samples? That's this throughput. So it doesn't include any training here. They're both trained offline.
So
Both have to be trained, but here they're both trained offline.
and this training is for a large number of symbols. That's what I'm asking. It's like not for like for every bit or every symbol that you transmit.
It depends on the self-interference channel, I mean, how it changes. You mean how often you have to do, or if you can do a training and then keep it the same for many thousands of symbols.
Right.
This depends on how this channel changes.
So if the
echo.
if the channel doesn't change, because is the channel dependent on the signal? That's what I.
It may be. It may be, I mean, it depends where you operate the amplifiers. But sometimes the nonlinearity of the amplifier can depend on the input signal.
Yeah.
So
how do
it
you
may
deal with
depend
that?
on the signal. In that case, you have a big problem.
Right.
If it depends a lot on the signal, then you have a big problem. You cannot do much. Anyway,
Especially with the
with any
IBM, which has a peak to average ratio.
yes, yes. But at 10 dBm with the amplifier we had, we didn't see such a problem. And I mean, it kind of worked, although we don't have a very big sample, so we didn't let it run for a few seconds to see if it still works. Yeah, that is a good point. Yeah.
I'm just curious. This is fascinating. I like it a lot. Thank you.
You're welcome. There are many problems with full duplex in general.
Yeah.
It's very difficult to make this work in practice. There are tons of questions. But yeah, as I said, this has to do with finding an efficient way to generate the cancellation samples. assuming that the training is fine and that the channel doesn't change too often and that you can actually implement this, that you can have a system that works like this, you need a good way to generate these cancellation samples. And what we show is that if you use this neural network approach, it seems to be a better way than the polynomial way to do this. That's the conclusion here. So as I said, we get same cancellation performance, in this experiment at least, with much lower complexity, both algorithmic and circuit complexity, as we show here. So with this, I can conclude. We can continue the discussion with as long as you like. But as I said in the beginning, I think that we need a combination of approaches to maintain the progress that we had in the past few years. I talked about some of them here: classical algorithm hardware co-design. The second one, the approximate computing one, I actually skipped, but we can definitely discuss that. And then the tools from other disciplines, I also skipped one of them, but I talked about how we can use machine learning in a very specific application to significantly reduce the complexity of the self-interference cancellation step in full duplex transceivers. And as I like to close with a positive sign, so the end of the happy scaling era that I described in the beginning. Of course, it creates many challenges, but all of these challenges are also new opportunities for innovation, in particular for researchers. They're probably a bigger headache for people in the industry. Yeah. For us, it causes, it creates many interesting new problems. Yeah, so that's everything. Thank you.